Thank you very much. I must admit I'm a bit daunted, having followed Adina and Kylie's presentations, which were both inspirational. So how can we follow that? Well, as you know, we're in the middle of an energy crisis at the moment, but it's not new. We've been through, in my lifetime, innumerable energy crises, and we haven't found a way to solve them yet. And the challenge is this: how can we provide secure, reliable, low-cost and low-carbon energy for the planet? We simply haven't found a way to do it today. Can space be part of the answer? And of course, the answer is yes, it can. So why do I have any credentials to talk about this? Well, first of all, my background, I spent a career in oil and gas and renewables. So I know a little bit about energy and the challenges of that. But secondly, for the last time, I've been leading Oxford Space Systems. So what do? We provide deployable antennas for space. You can see a couple of our antennas here. And what they're doing is they are transmitting radar beams in a very narrow beam down to Earth for Earth observation, and then tracking the signals coming back in order to give very high resolution day-night imagery from the ground for a range of applications, from floods through to sovereign requirements to have a look at their neighbours. So the capabilities and the understanding we have for these large deployable antennas are precisely those capabilities that we're going to need to solve the engineering challenges of solar power from space. We're going to need in-space manufacture. We're going to need in-space assembly, and we're going to need in-space deployment to achieve the engineering goals. Okay, so unfortunately, being the third speaker, you know some of the answers to the questions already. Why is space-based solar power? And the answer, as Kylie said, is a lot of it about. Okay, if you just look at the geostationary orbit, that's 35,000 kilometers above here, where satellites basically stay in the same place above the planet all the time. If we just harvest the power from that narrow strip of real estate, we can meet all our requirements for the next 30 years or so. And obviously that's just scratching the surface of what's available. So there's an awful lot of power there available for us from space that is carbon free for us. So next slide, bit techie. So bear with on this one, okay? So on the left hand side, you've got a satellite in space. You can see it there, and it's got three requirements. Oh, by the way, I should say, these slides were put together by the Space Energy Initiative. And a big shout out to Martin Soltay and Sam Adlin, who are the people who are running that. I'm on their advisory board, but I obviously take no credit for the work and the slides they've put together, which I'm using. But I will answer any questions you have. So the satellite on the left has got three requirements. It does three things. It's got large reflectors to capture the solar power. It's got a converter converting the light into radio waves, and then it's got a big antenna to transmit that in a narrow beam down to Earth. So as you can see, this is a pretty big antenna. It's nearly 2 kilometers across, okay, and about 5 times the weight of the International Space System. So we're talking about huge structures that we'll be putting into space to do that. And then on Earth, you can see on the right-hand side, this is a rectenna, another type of antenna. What this is doing is effectively capturing the radio waves and turning them electricity to go into the grid. And you've seen this superimposed on a wind farm just off the coast of East Anglia. So that's basically how to do it. Capture the sun, convert it into radio waves, beam it to Earth, and then collect it and put it in the grid. Obviously, that sounds pretty straightforward. It's very far from that. The engineering challenges, I know, are going to be immense. It's a 2 order of magnitude scale up from what we've done today with our deployable systems. Clearly, there's going to be engineering challenges to overcome, environmental challenges to look at. But so far, there are no roadblocks in the way we can do this. So you might ask, if it's such a good idea, why has it not been done before? Obviously, we heard about Jules Verne. In fact, Isaac Asimov postulated solar power from space in 1941. And NASA spent a few $100 million looking at it in the 70s and 80s. Clues, obviously, in the presentations you heard before, the cost of space launch, getting to space thanks to, and I apologize, this, as you know very well, isn't one of your reusable satellites. This is a SpaceX one. But basically, the vast majority of the cost of solar power from space is getting the stuff up there. It's the mass times the launch cost is a big proportion of the costs of an installation. And within the cost of the launch, it's the launch vehicle that's the bulk of the cost over and above the propellant. So really revolutionizing the launch technologies, which we've heard about, and there's more to come, I'm sure, is turning what was completely uneconomic into an economic solution. I'll talk more about that in a little while. Alongside that, there are other technology advances around hardware, satellites, PVs, space robotics, assembly in space, all these sort of things, composites that we're working on. Those are all enabling, but really the bulk of the game changer is around the launch costs. On the, if you like, the demand side of the equation, the climate crisis, climate emergency, the energy crisis, the waking up to the fact that energy security is an issue, is a driver. But to be truthful, those drivers have always been there in my lifetime. What's changed this now is the cost of doing this is now, it's now achievable. Here's a busy slide. So, if we can do this, what are the benefits? What are the attributes of solar power from space? Well, first and foremost, it's about electricity generation. And what we mean here is baseload power, always on power, and at a competitive cost. You've got to be, I think we heard from the nano technologies earlier, you've got to be low carbon and low cost to be competitive. Energy security is in the news now. So basically, you're having power that's beamed from space right down to the UK, with in fact a structure that's quite resilient to attack. It's a power that's safe, it's integratable, it's high load factor. You can actually switch it from one location to another if you need to. And the environmental impact, despite the cost of the fuel to get these structures to space, it's very low carbon footprint because it's lasting for a long time, high energy efficiency when it gets to ground, and the amount of land you need for it is pretty limited. And of course, this is a technology, it's an engineering challenge, but it's within our grasp to deliver in the next 20 years or so, gigawatt scale facilities, which we can use with all the other technologies, whether it be electric cars, whether it be, gas to hydrogen for homes. So it can be part of that zero carbon mix. So basically, the upside is space-based solar power. It's clean, it's capable, and it's deliverable. I said I'll talk a little bit about numbers. So cost of production. So if any economists in the room, this is a levelized cost of electricity. And as I'm just looking here at the low carbon technologies, and space-based solar power is the one at the top at £26 per megawatt hour, based on a not a particularly low discount rate when it's in the market and has been proven. Probably we're going to get a lower than the 10% discount rate we're using here. So compared against two other technologies, the top ones are the established low cost, low carbon technology we're using today, solar and wind, onshore and offshore wind, which are, they're good technologies, they're low cost. The issue, the drawback with them is that they're intermittent. They're not always on. And therefore, to run an overall low carbon system, you need either backup, storage, or some other technologies to back them up. So the all-in cost of those is quite a bit higher than the per unit cost. So that makes them significantly more expensive than solar power from space, which is always on 100% of the time. And then the three at the bottom I've used, this is gas, CGT is combined cycle gas turbine with carbon capture and storage. Relatively straightforward technology, frankly speaking, but pretty expensive. Nuclear, dedicated biomass, all of these have significant drawbacks of their own, which I won't go into now, but we all know what they are, and they're much more expensive. So just in economics terms, solar power from space is the winner here. So there we go. The UK BEIS has commissioned a study which Fraser Nash have completed, which concludes that it's technically viable. There are no environmental and engineering roadblocks to space-based solar power. We can get to net zero with it. It can be economic. So, we've just got to make it happen. How do we make it happen? It's going to need a fair bit of money, obviously, perhaps not in the context of how much we're having to spend on shoring up our energy bills this winter. But the first stage is really to develop the technologies, prove they work, do small scale tests to check them and to sense check the environmental issues and risks and check those are dealt with. And then moving to a small scale operating unit this decade, and the first gigawatt scale unit could be operational but by the end of the 2030s. So there we go. What are the next steps? People like you need to believe this can happen, and we need the funding from government and from private institutions to make it happen. And we need companies like ours, the others you're seeing today, putting their weight behind it to develop these technologies and just make it happen. So prediction, we're going to see gigawatt scale solar power in my lifetime, which hopefully is going to go on quite a long time. Thank you very much indeed for your time.